All right, my friends, welcome to section 3.3, part 1, basic differentiation rules. So this would be chapter 3, section 3 in the Calculus AB book, if you're wondering where that came from. But truthfully, all you really need to know this year is it's called basic differentiation rules. We'll be making worksheets for anything that you would have needed a textbook for the rest of the year. So it should all be notes and worksheets at this point. So hopefully that's good news for you. Okay, so example 1. And I think you'll be able to do example 1 right out the gates. So the directions are for you to differentiate each function. All right, now the word differentiate in like a math context right now means take the derivative of. So for part A, let's say I give you f of x equals 3. And then for part B, let's say I give you g of x equals negative 1.89. Okay, and when we say find the derivative and we don't mention a certain value, then you would know that we're talking about the general derivative. And if you think graphically about this, so if you were to think graphically about the if you were to think graphically about f of x equals 3, then you'd have this horizontal line. And an important fact that goes along with parts A and B and also example 2 is that a line graph is its own tangent line. So we'll just put a little clutter around that because that's kind of an important fact. So if you think graphically for a second about this, if this is its own tangent line, then what would the slope of the tangent line be at any x value, no matter what x value you're at? And so I'm hoping that you're okay with the slope of the tangent line at any x value would be 0, okay? So you're actually going to learn some pretty easy rules in chapter 3. What really the main work is going to be in understanding and using the notation correctly. So hopefully everybody's okay with f prime of x equaling 0 means that the slope of the tangent line to the graph of f at any x value would be 0. And how come? Because this was a line graph with a slope of 0, and a line graph is its own tangent line. Okay. Similarly, if you think about g of x equaling negative 1.89, here you're just dealing with another horizontal line. We'll just say, I'll add some notation to previous stuff. Anyway, so you're dealing with another horizontal line. A line graph is its own tangent line. So what would the slope of the tangent line at any x value be in this case? And I hope you're okay with it being 0. As well. So let's generalize what's happening here in the form of your first differentiation rule. So the rule is called in words the derivative of a constant function and in function notation, we would say if f of x is equal to c, and in this case by c I mean any given constant, then what would the slope of the tangent line at any x value be? And I hope everybody is okay with the answer being 0. Now, you could have gotten these answers also by using the definition of derivative that we learned previously, but I was hoping that just doing some graphical reasoning would also make sense. Okay, so this is how you say this rule in function notation. So let's actually go ahead and say that this is how you say this rule in function notation. And function notation is what is going to be your comfort zone because that's what we've been using all along. In this lesson, I'm supposed to also introduce you to something called Leibniz notation. So to say this entire sentence using what's called Leibniz notation, you would say the derivative with respect to x of a constant is 0. So just to make sure that we're clear, this entire statement is what it takes if you say it in function notation, and its equivalent in what's called Leibniz notation is this short statement right here, okay? All right, and I'm a big believer in if you can say it correctly, you will do it correctly. And so in your mind, when you're doing math by yourself and you're reading this, or right now out loud, since hopefully no one can hear you, or if they can hear you, you don't care what they think, we're gonna read this together and make sure that you can say it correctly, okay? So we've got a couple different ways to read this. So the D on top would be the derivative, and then on the bottom, the dx is the d is like with respect to, and then x of c, where c is a constant, is 0. Okay, so starting from the beginning, the derivative with respect to x of a constant is always 0. Okay, and this is again Leibniz notation. From here on out, you're going to be held accountable for using function notation or Leibniz notation correctly, depending on how the problem is started. So you want to, as quickly as possible, get as comfortable with each one, okay? All right, my friends, so this is your first derivative rule, and I hope that it feels true. It's not the kind of thing that you're just memorizing and not understanding. Okay, now, if anybody ever wants you to prove it, let's practice just kind of proving this statement. So let's say, let's do this in function notation this time. Let's say f of x is equal to c. Then, what would f prime of x be by the definition of derivative? Well, it would be the limit as h approaches 0 of f of the quantity x plus h. Well, if this is f of x, what's f of the quantity x plus h? Well, it's c minus f of x, which is c all over h. And then that would equal the limit as h goes to 0 of 0 over h. And so, which then, since h, by the way, is not exactly 0, it is just a number infinitely close to 0, you basically have 0 divided by a non-zero number, so you'd have 0. So there you go. Limit as h goes 0, 0 is still 0. And so we just proved if f of x is a constant, then f prime of x will be 0. There we go. Okay. Now let's kind of take this concept and just move into something a little more dynamic, nothing crazy. So let's talk about example 2. Directions again are differentiate each function. Remember what the word differentiate means in this context? So for part A, the function is f of x equals 2/3 x minus 17. Part B, let's give you g of x equals 8 minus x. Okay, so you could use the definition of derivative as you memorized it for the chapter 11 test on these. It would give you the answers, or you could think graphically. Remember, a line graph is its own tangent line. So if you were to graph this, it would be a line graph. And if it's its own tangent line, then I hope it makes sense. The slope of the tangent line would be 2/3 no matter where you're at. So for part A, we could say f prime of x would be 2/3. Same thing here, g of x equaling 8 minus x, that's also a line graph. A line graph is its own tangent line, so the slope of the tangent line to this graph would always be -1 at no matter what x value you're at. So here we have our two answers. So if we were to generalize this situation, we would have a rule that would give you the derivative of a linear function And we'll show this in both notations just to get you used to it. So first in function notation, we would say if f of x is defined as mx plus b, then let's think of this as a fill in the blank. What do we think f prime of x would be? Well, this is a line graph. Its slope is m. A line graph is its own tangent line. So the slope of the tangent line at any place would be m. All right, now, so this is how you say this using function notation. Now, let's talk about how to say this entire sentence using what's called Leibniz notation. Okay, so in Leibniz notation, to say this exact same thing, we would say if you take the derivative with respect to x of anything of the form mx plus b, you will always get m. Okay, two ways to read this. We're going to practice with me. The derivative with respect to x of mx plus b is m. Or you could say, this is like a nickname, but it's totally math acceptable, ddx. Sounds like I'm stuttering, but I'm not. I'm going to say it again. ddx of mx plus b equals m. Okay, both mean the same thing. I think in your head saying the derivative with respect to x is most likely way better for you, because man, oh man, can this stuff get more interesting and more complicated, and knowing what it means, what it truly means, is probably the most empowering thing for you. All right, my friends. When I put this memorization cloud around it, I do hope that this is something that feels true, just using the fact that a line graph is its own tangent line. Okay, practicing a little proof work for you. So if I asked you to prove this rule, then you could say, and you could practice this using function notation like last time, or you could practice using Leibniz notation. I think I'll go ahead and stick with function notation for now, because that's probably your comfort zone. So you could say if f of x is equal to mx plus b, then now we're going to use the definition of derivative. F prime of x is equal to the limit as h approaches 0 of m times the quantity x plus h plus b minus, and now we're going to do minus f of x, so minus mx plus b, all over h. All right, limit as h goes to 0, distribute, we'd have mx plus mh plus b minus mx, so I'm just distributing this right now, minus b, all over h. Okay. Notice the b's vanish, the mx's also vanish. So what are we left with? We're left with the limit as h goes to 0 of mh over h. The h's cancel. You're left with the limit as h goes to 0 of m. As far as this limit is concerned, m is a constant. So if h can go to 0 all at once, m is still going to be an m. And so there we go. Bring your prompt down. We just proved if f of x is of the form mx plus b, then the slope of the tangent line at any x value is just m, which I hope makes sense on a graphical reasoning level as well. Okay, now let's have a little chat about notation, and then we'll take this to the next level. Okay, so a little refinement on the topic of notation. Okay, first thing, what two types of notation do we have? Think of it as two different dialects of the same language, and you have to learn both. So you'll need to be comfortable with function notation, and then you'll also need to be as comfortable eventually with what's called Leibniz notation. Okay, so a quick, just kind of a side-by-side example. So in function notation, you'll know that you're supposed to use it because they'll use f of x type notation when they give you the original function rule. So That's your trigger that you get to use function notation, okay? Now, when you take the derivative with respect to x of both sides, on the left side, if you take the derivative of f of x, you get f prime. So I'm just going to go ahead and like put an arrow that says we're going to take the derivative. So on the left side, you'd get f prime of x. And then on the right side, if you take the derivative of the right side, this is a linear function. The slope is negative pi, so you would just get negative pi. Let me write that so the negative's a little more obvious. There we go. So you'd end up with negative pi. So if they give you f of x or g of x or h of x type notation, then you get to just call your derivative that function rule prime, you know, of x type stuff. So this is probably what you're used to and probably what you like the most right now. But there will be times, and they're not too far down the road, when function notation is not going to work very well, especially when we get into like related rates work and things like that next year. And so you'll want to be able to, at this point, say the same thing using Leibniz notation, okay? First thing, when is it you're gonna need to use Leibniz notation? It's when instead of using f of x, they use y. That is going to be your trigger to know that you need to use Leibniz notation, okay? Now, what I'm going to illustrate here in the next step, I'm going to show what it looks like to take the derivative of both sides. It's a step that you would not need to show, but you would need to think it in your head. So in Leibniz notation, you can show I am going to take the derivative with respect to x of the left side. And remember, if you change one side of a balanced equation, you'd have to do the exact same change to the other side. So that would mean you need to take the derivative with respect to x of 8 minus pi x. Now, I will oftentimes refer to this step that I just showed as kind of like dirtbag math because we really didn't do anything. We just said we would later. So this is us saying, I'm going to take the derivative with respect to x of both sides. Okay, now it's a matter of like just doing it. So on the left side, we would say d dx of y is called dy dx. Okay, that's the notation for that. So these two are equivalent. Okay. Now let's talk about why that makes total sense. Remember the long way of reading this. The derivative with respect to x of y. Well, this has a long way of reading it as well. It means the derivative of y with respect to x. So I'm going to say that again. I want you to listen to how they definitely are the exact same thing. The derivative with respect to x of y. The derivative of y with respect to x. Those are their long names. Their short names are d dx of y and dy dx. Okay, now on the right side, what's d dx? What's the derivative with respect to x of this linear function here? Well, it would just be negative pi. And I'm going to make my negative look like it's a negative. There we go. Okay. So we just did the exact same thing in two different dialects. This is how you express your answer in function notation. This is how you say the exact same thing in Leibniz notation. Funny story, if you think about this is supposed to be a formula for slope. dy means change in your y variable or your rise, and dx means the change in your x variable or run, rise over run. So in a way, this notation is a lot more descriptive than the one that you're used to. Okay, now oftentimes folks, when they first learn this, that would be you guys, folks get d dx confused for dy dx. And I hope that even if you already have those two straight in your mind, you can see why some people get them confused. And we want to get you past that confusion because it's important that you can tell the difference between the two. So if you see d dx, it means you haven't taken the derivative yet. And so d dx means basically kind of like I owe you a derivative. I haven't done it yet, but I'm going to. Now, dy dx, it means that you did d dx of y. So you did take the derivative, and this is what you got. So if you see dy dx, that's what you have after you differentiate. Subtle, but important. So d dx means I'm going to take the derivative. dy dx is what you got after you did it. Okay. All right, my friends. And if it doesn't make total sense now, just keep working on it. It will come along. Okay? All right, let's move into taking this to another level. So example 3. We're going to do example 3 by using the definition of the general derivative. So the directions are for you to differentiate each function. Okay, I lied just a little bit, sorry. Part A will give you f of x equals x. That's just a linear function. So you could do that without working too hard. So this would fall under the category of like a mx plus b situation. So you could think of it as, if you want, as f of x equals 1x plus 0. You do not need to write that step. So what would the slope of the tangent line be at any x value? I claim the answer would be 1. I hope that makes sense. Okay, now let's look at part B. Part B, let's say f of x is equal to x squared. Does this fall under the category of any of the rules that we've established? So far in these notes, we've established the derivative of a constant. X squared is definitely not constant. And we've learned the derivative of a linear function, and x squared is a parabola, not a linear function. So in that case, we would fall back on the formal definition of derivative. And so we'd say f prime of x is the limit as h goes to 0 of f of the quantity x plus h would be x plus h squared minus f of x is x squared all over h. We then have the limit as h goes to 0 of x squared plus 2xh plus h squared minus x squared all over h. Okay, the x squareds will vanish. Everything else in the numerator has a factor of h, so I'll show factoring it out. So we'd have the limit as h goes to 0 of h times the quantity 2x plus h all over h. The h's cancel. You'd be left with the limit as h goes to 0 of the quantity 2x plus h. And then the remaining h goes to 0 and you just have 2x. So we found the rule for f prime is 2x. Okay, I think we will do 2 more. So part C, let's do, what if I give you f of x is equal to x cubed? Okay, not a constant function, not a linear function. We haven't established a rule for it, so we're going to fall back on definition of derivative. All right, so let's see if you're good at this. Let's see how fast you can go. F prime of x is equal to the limit as h goes to 0 of the quantity x plus h cubed minus x cubed all over h. Expanding x plus h cubed, the easiest way would be to use Pascal's triangle where the coefficients are 1, 3, 3, 1. So you'd have x cubed plus 3x squared h plus 3xh plus 3xh squared, that is, plus h cubed. Then you have minus x cubed, bring that down, all over h. Okay, the x cubes vanish. Everything else on the top has a factor of h. All right, hopefully you're not here to give me your permission, but I'm going to pretend you did. I'm actually going to, instead of showing this step where I factor it out and then cancel it, I'm just going to divide the h's in and kind of cancel it out. So 3x squared h divided by h is 3x squared. 3xh squared divided by h is 3xh, and h cubed divided by h is h squared. So I hope it makes sense. That's what I'd get after I factored the h out and then canceled the h's. Okay, let the remaining h's go to 0, and who's left standing? This term would go to 0 because it has a factor of h, and then this term would also go to 0 because it has a factor of h. So as far as this limit's concerned, 3x squared is a constant. So h can go to 0 all at once. 3x squared is still going to be 3x squared. So, whoops, so we got f prime of x would be 3x squared. Okay, so part D, actually, you know what, before we do part D, let's create a table and collect the information that we have here. So let's say, I'll do this on a separate sheet of paper, I think, yeah. Okay, so let's say we, for example 3, we make a collection of information. I'm going to make a table. In the first column, I'll collect what f of x was. And in the second column, we'll collect what we got for f prime. So for part A, f of x was x. For part B, f of x was x squared. And for part C, f of x was x cubed. So if you collect our answers, so when f of x was x, f prime of x was 1. When f of x was x squared, f prime of x was 2x. When f of x was x cubed, f prime of x was 3x squared. And the reason that I'm having you put this information in a table is because there's a fun little pattern that you could pick up on, and it's going to turn into a huge shortcut for folks. So, so if you think, it's probably easiest to see the pattern here with x cubed. So notice that when we took the derivative, the exponent was the coefficient, and then you had a 3, but now you have a 2. And then see if you can come up with a pattern that would work to kind of, or a formula that would work for how to get from here to here. And then it would have to work though for all of them. So let's look at x squared. Your exponent is 2. Notice it becomes the coefficient. And then your exponent on your derivative was 1, which is 1 less. And then funny story, this was x to the 1, and I know you don't really need a new rule for that because that's a linear function, but so that's x to the 1. If you were to take that power, make it be your coefficient, and then subtract 1 from the power, you'd get 1 times x to the 0, which would be the 1 that you had. So, so think about what should the derivative of x to the 4th be if you were to just try to do, like, kind of pick up on the pattern here that we've established so far. So think about that. And then for part D, we're going to do it the long way and then see if you're right. So for part D, let's say f of x is x to the 4th. And then you want to figure out, you want to differentiate it. So f prime of x then, what would that be? It would be the limit as h goes to 0 of the quantity x plus h to the 4th minus x to the 4th all over h. That would then turn into the limit as h goes to 0. Expand that using the Pascal's triangle 1, 4, 6, 4, 1. So we're going to go x to the 4th, one of those, plus 4x cubed h plus 6x squared h squared. Oh, I'm going to run out of room. Plus, no, I'm going to move this to the left. Sorry, guys. Sorry. Okay. Equals, sorry. Limit as h goes to 0. Let's see, x to the 4th plus 4x cubed h plus 6x squared h squared plus, oh, I'm still not going to be able to fit it. Good night. 4x h squared. Okay, this is horrible. Plus, cubed plus h to the 4th. All right, minus, okay, this is, I think, the expansion of x plus h to the 4th, minus x to the 4th, beep, all over h, and that is not a good way to write that, just so you know. All right, so then let's see, x to the 4ths cancel. Everything else has an h in it, so I'm going to divide the h in. We'd be left with the limit as h goes to 0 of. H goes into 4x cubed h, 4x cubed times. H into 6x squared h squared would be 6x squared h. H into 4x h cubed would be 4x h squared. And h into h to the 4th would be h cubed. So as h goes to 0 now, anything with an h in it, a factor of h, all of these guys would all go to 0 as h goes to 0. So the only one left standing would be 4x cubed. Sorry, the spacing's so bad. Okay. Anyway, so if you were thinking, hey, look, it looks like we're just taking your exponent, it becomes your coefficient, and then whatever power you used to have, you would subtract 1 from it, and you thought f prime was going to be 4x cubed, then you have officially picked up on the pattern known as the power rule for derivatives. So let's just check and see how you're doing with this. So what if we were to say, what about x to the 42nd power? Well, I hope we're all grateful for not needing to do this anymore. So if you were to use this pattern, then you would get the derivative to be 42 times x, and then take 1 away, and then to the 41st power. So that would be your derivative. So now let's say what this would be in general. So in general, if you have x to any constant power, I'll just use n to mean kind of a constant value there, then what's the rule for the derivative? So if this is a constant, then you'd have n as the coefficient times x, and what would your new exponent be? It would be the old number take away 1. Okay, so let's make this official. This is called, as promised, the power rule for derivatives. And we're going to say this in both dialects. First, let's use function notation. If f of x is x to the nth power, then what's f prime of x going to be? It would be n times x to the n minus 1. Okay, that's how you say that using function notation. All right, now I want everybody to think about how would you say that using Leibniz notation? Okay, and let's see if you can write it before I do. I'll give you a second to think about it. Okay, so to say the exact same expression using Leibniz notation, you would say, if you're taking the derivative with respect to x of x to the n, you will get n times x to the n minus 1. Now, funny story, a lot of people really like the power rule. And if that's you, then that's great, but you don't want to like it too much. So some people just kind of think, oh, derivative is going to be, and so they learn this side better than they learn this side. But it's really important that you know that this rule only applies to this very prescribed condition. You're taking the derivative with respect to x of something in the form where your base is exactly x, no more, no less, and then of to an exponent where your exponent is a constant. So some folks like this rule so much that they go around trying to use power rule on something that really wasn't even of this form in the first place. And so I think the saying is, I had a friend that would say, to the man with only a hammer, the world is a nail. So you want to make sure that before you use this tool on a certain job, that you have the right kind of job for it. So when you memorize this rule, and it is easy to memorize, make sure you focus on both sides of the equal sign, not just the right side. That'll just get you into big fat trouble. Okay, let's do an example that practices this, and then we will transition from there. Okay, example 4. Oh, you knew the directions were going to be differentiate each function. Okay, now one thing I do want to make sure people realize is that the point of this lesson is to transition from needing to use the definition of derivative all the time to having rules that you can use instead in the right type of prescribed conditions. So a lot of people in the past have gotten confused and they thought they had to keep using the definition of derivative all the time. The definition derivative is there for you for when we get into situations where you don't have a rule for it. But you do want to make sure that you can do both the rules and the old definition. So, okay, example 4, differentiate each function, and part A is y equals 1 over x squared. It's very important that you stop and do what you're going to do with it, and then you watch what I'm going to do. So with that said, notice a couple things. There's a lot going on here. Number one, what type of notation should you use for your work? They called the function rule y instead of f of x, so we're going to need to make sure you can do this using Leibniz notation. So really, and I do think for now you should probably show this, we're going to take d dx of both sides. So let's just show that, okay? Also a note, we always write d dx on the left side because it is a function, and we never say x of f. We always say f of x, so functions go on the left side of things, never on the right, okay? So we're going to take d dx of both sides. Now on the right side, I ask you, does this look like your power rule situation? And the answer, my friends, is not yet. And so we're going to practice the art of algebra before calculus. So what we're going to need to do is we're going to need to write this in a form that looks like this before we apply this rule to it so we don't get some crazy answer. So we'll rewrite this as still d dx. d dx still needs to sit there and wait. And 1 over x squared is just equal to x to the negative 2. And in my opinion, this is why negative exponents exist, is so that we can move forward in this situation. On the left side, the notation for d dx of y that's simple and that you want to use for your final answer is dy dx. Okay, so our answer then would be dy dx equals, now we can use power rule on this. Now you can, because this fits this description. So we would have negative 2 for the exponent times x, and then your old exponent was negative 2. If you take 1 away from it, you get negative 3. Now, a little twist that some people don't expect, since the original problem was not written in negative exponents, we turned it into negative exponents so we could use the rule we like on it. Your final answer should actually be written back in the convention of the form that it was in originally. So the answer that you would want to make sure you can write it in is negative 2 over x cubed. Now, this is technically correct, but you do want to make sure you can get it into this, because my friends, if this was a multiple choice problem and you could do all of this and then you seriously circled none of the above because you didn't notice a little algebra 1 on your own answer, that would be a very sad situation and worth avoiding, okay? All right, let's do same thing, but part B. Part B is going to be y equals the cube root of x. Same thing, I recommend that you go through this problem on your own. I'll try to make this look a little bit more like a cube root there, and see what you can do, okay? So, so assuming you've paused the video and done what you can on it, the question here is this something we have a rule for, or do we need to fall back on limit process type work? And so is this a power rule problem? Not yet, but a little algebra before calculus would allow you to rewrite the cube root of x as x to the 1/3. Now it is a power rule problem because we're going to take d dx of both sides. So d dx of y would be equivalent to d dx of, and we're just going to replace the cube root of x with x to the 1/3. So on the left side, we'd have dy dx. On the right side, we'd have 1/3 times x, and then take 1 away from 1/3, and you get negative 2/3. All right. Now at this point, you have done the rule the use of the rule correctly. The challenge is going to be rewriting this so that it is back in radical form, and not just in any radical form, but reduced radical form. So let's make sure you can do the algebra to get there. Some folks have said in the past, it's not the calculus that'll get you, it's the algebra that'll kill you. So let's make sure the algebra doesn't kill you. So if you were to write this in moving toward reduced radical form, one thing I'd recommend is getting rid of the negative exponents. So this would equal 1 over 3 times x to the 2/3. And then you could put this back in radical form now. It would be 1 over 3 times the cube root of x squared. So just a reminder, the denominator defines the type of root. The numerator is the power that's on your x value there, or your base. Okay? And then the last thing, let's make sure that you would know how to rationalize this denominator. I'm going to get a second color out and demonstrate that.
Mama?
Yes, dear?
How long is this?
I have to finish this video and then I can.
How many?
How about if I finish this example and then I'll stop the video and finish it a little later. Does that sound good? Okay. Always sounds good to everybody. All right, so let's multiply this by an appropriate version of 1. Now, I'm going to show you the wrong thing first. Common, very educated, incorrect answer is multiplying by this, okay? But let's talk about real quick why that will not work. Cube root of x squared times another cube root of x squared, my friends, is cube root of x to the 4th, which would be x times the cube root of x. So you have not rationalized the denominator. So let's think of it this way. How many, look at the denominator, how many x's do you need in here for it to cube root perfectly? The answer is 3. You already have 2. So you'd need to multiply, my friends, times just the cube root of x over itself. Because you have 2, you just need 1 more. Okay? All right, so now we would get dy dx is the cube root of x over, and then on the bottom you'd have 3x. All right, and we are doing this because if this was a multiple choice problem, you would need to be able to pick something like this out of the lineup. And just doing power rule and getting this far would absolutely not get you where you want to get to. So practice this little algebra with me, okay? Make sure that you can do the algebra and not just the calculus. All right, my friends, this is not the end of what we need to go over. We have a little bit more stuff to go over. I think you're going to find the homework that goes with this refreshingly easy. You're going to do all the hard work in the notes, but I'll have a video coming for you soon to finish this up. Take care, everybody.